So we have seen how public key cryptography can be used to provide confidentiality, and how this can be used in combination with secret keys to provide hybrid encryption. Similar to what we have seen with symmetric cryptography, we can use also public key cryptography to provide authentication. This is the topic of this new section. It is called digital signature. The setting is exactly the same as before when we want to add a tag. In the context of public key cryptography, the tag is called a signature. The only difference now is that the keys are not the same. So on the sender side, we have a message that we want to authenticate. We use the private key of the sender to add a tag called a signature here. This is transmitted in clear text with a message. Of course, we can additionally encrypt, as we discussed before. And then on the receiver side, we will verify, and the verification is using another key, which in this case can be public here. So the combinations of keys are, as usual, one key is public, the other is private. And here, obviously, the key that needs to be private is the key done by the signer, because this is only in this way that anybody can verify that the only entity that could plausibly create this tag, this signature here, must own the private key. So this provides a number of features similar to what we had with authentication tags, with one additional property. It's called public verification, because now the public key, as the name indicates, is public. So anybody can verify that this message must have been sent by this guy. So if you go to a website that pretends to be a given shop or a bank that says, here is the cost or the price of such a service, then you can verify, if you know the public key of the bank or the shop, that this must have been sent exactly by this entity here. With RSA, it works because of what I alluded to a few minutes ago, that is the commutativity of decryption and encryption. We have seen that if I encrypt with RSA with a certain key, which is public or private here, I can decrypt by taking the other key. But it works in both ways. I can, here, for example, if I put a signature, the same computation I would do to decrypt if I consider M as a ciphertext, which of course M is not a ciphertext, is a plain text, but I apply the decryption mechanism here, dk of M, then at the other end, I will use the same algorithm that was used for encryption. And this is because RSA is using exponentiation. Remember that for encrypting, we put to the power E. So here for signing, we put to the power F, and the receiver side will put to the power E, and this is a public thing here. We need only the public key, and the exponent here, E, is a constant of the scheme. It's not at all secret. And of course, M E to the F is MF to the E. So this is the basis with which it works. So to make a long story short, the digital signature, which is not here, should not be T, but S, is M to the power F here. And the F, of course, as we have discussed before, is an exponent that is secret. In order to compute it efficiently, you need to know the private key, i.e. the factoring of capital K into its prime factors here. Now, this is the basics, but in practice, there is another element of the zoo of elements of cybersecurity that we need to introduce now is the hash function. So we have seen encryption with AES, secret key, how it can be used in chaining mode to provide practical encryption systems, how it can be used also to provide authentication MAC. We have seen also encryption using asymmetric cryptography, and decryption, and how by combining in a different order we obtain an authentication mechanism. In addition to all this, there is a central type of function in security, which is called a hash function. Unlike all the functions we have seen before, a hash function does not have a key. So a hash function is again one of those magic mathematical things. It's also called a one-way function. So a hash function is something that transforms a message M into a block, which is typically smaller, in a way such that it is impossible to infer any information on M by seeing the hash D here. D is called the digest when we apply it with a hash without any key. So a hash function maps a message of any length to a short block of k bits, which is called the digest. For example, with RSA, the length is 256 bits. And the crux is that the hash function is such that the digest appears to be randomly chosen among all possible values. If you change one single bit in the message here, that will completely change the digest in a way that, at least in theory, should appear to be completely unpredictable. In particular, if you see two messages, M and M prime, and you see the digest of the first message, then it's impossible to infer what the digest of the second message is. Which means in particular that if you, it's possible to compute the digest because you know the hash function, but the other way around, if I give you the D prime, it's impossible to infer what were the changes to the message that caused this D prime to occur. Of course, it is always possible by brute force, but a good hash function is one where there is no method better than brute force to find out what was a possible message M that could have created this digest here. As you know, hash functions are used everywhere in cryptography. Systems like Bitcoin rely heavily on hash functions. So what the miners are doing, they are computing by brute force solutions to the problem. Given a digest D, find a message M that provides this hash function. And today it's not known how to do that other than with brute force. Which means that's the virtue of exponential growth. If the length of the digest increases, then the difficulty of the problem increases exponentially. That means with sizes reasonable, like even a few hundred bits, the problem becomes truly astronomical, and even the Bitcoin miners will not be able to solve it. So a hash function is like a Mac from the viewpoint that it translates a large message into a small one, but there is no key. In a hash function, there is no key, and everything is public. The hash function is a well-known algorithm. All our computers have implementations of the standard hash functions used today in cybersecurity. Now, the hash function will typically be combined with a signature scheme, for example, RSA, a public key cryptographic system, where we will apply the public key calculation, not to the entire message, but to the hash of the message. So we'll first translate the long message into a short digest, and we will sign it. Again, this is because public key cryptography is very expensive. So we have here a hybrid digital signature scheme where we first reduce the complexity by using a hash and apply the public key cryptography to the hash alone here. Let's see what are the potential issues with hash function. Here is, for example, a hash function that is a bit like the ideas behind RSA, is using modulo P arithmetic. So here P is 257. So Homer invented this hash function. The hash functions of this type were proposed in the past. So here is, for example, a long message. The hash produces here a number that's between 0 and 256. So here it is F7 in hexa, for example. Now, if I change the destination account number, the hash function should change. But now, if I am tampering with the message, I would like that the hash does not change, because the hash presumably will be signed with the private key of the sender, and I don't know the private key of the sender. Therefore, I cannot compute the new value of the signed hash. So what I can do as an attacker is make sure that I transform the message such that the resulting hash remains the same. Now, Not surprisingly, we've seen last week that if we take a simple modular scheme, it can be broken easily because, in fact, everything is linear in modular arithmetic. And in particular, it's possible by adding the appropriate number of empty spaces, which is what the attacker has done here. I add empty spaces between the letter. The empty space is a character that transforms the hash, and I can compute by solving linear equations how many empty spaces I need to do such that the hash is not modified. So the original message, if I don't put the empty spaces, I modify the hash. Now I can correct this by adding enough empty spaces, which I did here. I changed the number. I compensated for the number here by adding empty spaces, and those two errors that I did, they compensated. And this is doable by solving linear equations. I know the impact on the hash system of my modification. I know the impact of every insertion of a blank character, so I can compute it. This is what I did, and I obtained, of course, a message that was had the same hash, and therefore, when it will be signed using RSA, for example, the signature will be correct. So this is a successful attack against a signature scheme. Of course, this is what we call a collision. I had a collision here in the sense that I was able, from an original message, which is this one here, to an intermediate modified message, I was able to forge a collision. A collision means another message that has the same hash as before. If I can control the collisions, of course, the hash system doesn't work. So a good hash function should be collision resistant. Of course, you cannot be more collision resistant than by brute force. So it is always possible to mount an attack by trying all the hashes, but this we discussed already. So cryptographic hash functions are really at the heart of cryptography today. There were many in the past. Some of them are used. For example, MD5, SHA-0 are used even in some computer networking protocols, but they were broken at some point. So today you need to use hash functions, for example, SHA-2 or SHA-3, that are known to not be broken today. That's very embarrassing if you think about it. That means that there is no mathematical proof of the correctness of a hash function, or in fact of all security. All mathematical proofs of security of a system are always within a model, so assuming something. For example, if we assume that it is impossible to factor a prime number into an integer into its prime numbers in reasonable time, then RSA is secure. But whether the hypothesis that we made to draw this conclusion holds or not, this we don't really know. The only thing we do today is to rely on the security research community to screen by trying all possible attacks, also by proving things, so reducing the proof of attackability to hypotheses that can be more easily verified in order to know whether something is secure or not. I mentioned last week that cryptographic systems like symmetric cryptography that were believed to be secure, that were used for decades, like the DES, were at some point found to be insecure. So the same happened to hash functions. And this is why it is important to, the side effect of this and an important consequence is that you cannot design a system, make it secure, and believe it will be secure for a long time, which is a problem in the context of smart grids and industrial networks in general. Equipment in a smart grid has lifetimes that are in decades. A transformer can live for 50 years, but if there is a computerized part in it, if we have a smart part of the grid where we use computers to exchange information, then this computer part, this IT part, information technology part, will need to be secure, and its security is always temporary. So you need to update the software for security reasons. And most of the updates, we all have smartphones and computers that receive software updates every week or every few weeks. The major reason for that is, of course, it's not said very loud, but some problem were found either in the implementation or in the use of a security function where an algorithm must be changed. So whatever we do that requires secure software will need to be updated, which is a problem for hardware in particular. If you do hardware encryption somewhere, then you will not be able to so easily change your hardware. So that's one of the difficult issues in smart grid and in industrial networks in general today. Voila, a little quiz. A PMU signs a message sent to PDC. Now it's for authentication, right? It uses RSA just to make sure that an attacker is not tampering with the message. If we do this, which key should the PDC use to verify the message? I close the poll in a few seconds. And the majority says A, which is the correct answer. Oops. The PMU was presumably signed with something that must be secret to the signer, so it's the private key. And it must be the PMU's private key, because the only private key that you know is your private key. So the PMU was signed, the message was signed with the private key of the PMU, and therefore to verify its authenticity, you use the PMU's public key. There's no other way around. Another quiz here. So let me help decrypting the quiz. So I assume I have here two messages, M and M prime, that are long, and I compute the first C is a CBC AES tag. So that's a tag, as we have seen last week, that uses AES in chaining mode to obtain a verification tag, and with a secret key, little k. I have two different messages, M and M prime, and I receive two tags, C and C prime. And the first question which is asked is, if we see that the two tags are the same, does it mean that the messages are the same? If you believe so, then answer A is correct. Now I have two other elements. I have T and T prime. So T is HMAC SHA-512 K prime. So what does that mean? SHA, as we have seen, is a hash. But a hash doesn't have a key, but here there is a key. So here it is a HMAC, which is an authentication mechanism like CBC AES. So an alternative to using an encryption mechanism to provide an authentication tag is to use a hash. And this method, for example, consisting in XORing the hash with the key K prime. So I hash the message, I do the XOR with the key, and then that becomes also an alternative way of creating an authentication tag. If you want to verify the tag, you need to know the secret key, K prime. So you first XOR the received hash with K prime, and then you apply the hash, and then if everything is correct, that authenticates the message. So this is a second mechanism derived from hash to produce an authentication tag here. So same question, if T is equal to T prime, does it mean that M is equal to M prime? Third question, D is SHA-3 applied to M. So SHA-3 256 is another version of SHA. So it's a hash. Here there is no key. It's a pure hash. Is it true that if D is equal to D prime, then M is equal to M prime? Well, so what do you think? Which of the statements A, B, C is true? I close the poll in a few seconds. In 10 seconds. Closing. And the majority says A and C, which unfortunately is not true. So the correct answer is no. In fact, whether there is a key or not here doesn't change anything. So symmetric encryption is invertible for who knows the key. Oh, sorry, so that was encryption. So because of the nonce, it's not true. For tag or we have seen that collisions can occur in theory. It's hard to do if you don't know the key, but knowing that the tags are the same does not mean that the messages are the same. And the same is true for a hash function. So we have seen the basics of public key cryptography, how it can be used to encrypt, but how in practice we use it to produce a secret key for hybrid encryption. We have seen also how it can be used for authentication, and also how in practice we use a hash to authenticate only the hash. Now let's see what can happen. We will see that it's not sufficient. All the building blocks we've seen still have a problem. Assume you go to your bank. So Lisa goes to the bank to do some transaction. We have seen that we will create session keys for encryption. Of course, you can do the same thing for authentication. So you will, using the public key of the bank, Lisa will generate random keys L1, L2, will send them encrypting to the bank. The bank and Lisa know a shared secret without revealing anything to anybody in the world. And therefore, we can do authentication and encryption, and we can combine them in whatever way we want, like we discussed an hour ago. So perfect, that seems to work well, except now a man in the middle can break everything. So assume the bad guy here does the following. The bad guy inserts himself into the line and intercepts all communication. For example, you break the Ethernet cable or the optical cable that goes out of your house, or the Ethernet cable between your modem and some device of that goes through the walls of the basement of your building. You put a bridge in the middle and or a computer, and like we do in the labs, you can read all the messages and transform them. What the bad guy could do is send when Lisa goes to the bank. In fact, Lisa does not go to the bank because the bad guy is in the middle, and will reply saying, yeah, I am your bank, and here is my public key. Therefore, Lisa will encrypt with the public key of the bad guy instead of the public key of the bank. Now, to the bank, the bad guy will pretend to be Lisa. So the bad guy will receive the public key of the bank. Lisa will create secret keys that are secret and shared between Lisa and the bad guy. And the bad guy will reveal the secret keys that were created by Lisa, will propose them to the bank, and then we'll have an encrypted communication with the bank here. And whenever Lisa sends a message to the bank, encrypts it with those secret keys, but of course the bad guy knows the secret keys, can use them or other keys that it has created with the bank to send them with the bank, and then the bank believes they are talking with Lisa, and Lisa believes she's talking with the bank, but in fact both are talking with the bad guy. So that's called the man-in-the-middle attack, and this breaks all the security we've seen before. And in particular, all the secret session keys are broken. They are known by the guy in the middle and can be forged. Why is it possible? Well, this is because Lisa was assuming that the public key she sees is that of the bank, right? And of course it was not. It was the public key of the bank. But how do you know that the public key is the public key of the bank, right? Because the public key is a long list of hexadecimal digits, right? So how do you know it's the correct key? Well, you can say you can authenticate the key, okay, but then you have a chicken and egg problem. So how do we solve this? Well, it is solved by going back to the egg, or the first chicken, if you want, using what is called third-party certification authorities. Certification authorities are companies that guarantee the identity of other companies, and that provide what is called digital certificate. So a digital certificate for Lisa's bank, for example, would be a piece of text like this that would contain the official description of the entity, which in that case is a Swiss company. So any Swiss company has a number obtained from the Registre du Commerce, which you can obtain by sending a letter to Registre du Commerce Bernois. And you will be able to obtain, so Global Sign, for example, is the signer, can verify this. And then Global Sign will agree with the Banque Cantonale Bernoise about a public key. So the public key will then be signed with the private key of Global Sign here. Now, of course, that's again a chicken and egg problem. So here we're not really solving the problem. We're just putting all the complexity at one place. Of course, this will be a very complex procedure where perhaps people need to move physically to check who is the identity of whom, show IDs, or perhaps somebody of Global Sign goes to the Banque Cantonale Bernoise, or the Banque Cantonale Bernoise sends a document that is verified by a notary. So that's a heavyweight procedure that will be used to obtain a signed public key. So in essence, a digital certificate contains the public key of the entity and the signature signed by another party whom you trust. So you believe you trust it. So who trusts Global Sign? Well, for example, Apple and Microsoft and Google trust Global Sign. Because the software you receive comes from Apple, Google, or Microsoft, then your software will be trusting this entity. And the verification, the signature, verifies the public key, but also the identity, this whole, as described here. So it is binding the public key with the identity. So when your browser will now display that you're going to the bank here, this identity is displayed here in your browser. And this closed padlock means that your browser had a certificate that it could verify. So now it's up to the user to make sure that if you don't get this green signed symptom here, then you're not using something that is secure. Good browsers will refuse or send an error message if when they go to something that is sending a certificate, it obtains a certificate that cannot be verified. So when Lisa goes to the bank, she does not simply get a public key, she gets a certificate. Now the certificate is checked by Lisa's browser by verifying that the signature is correct. And to verify the signature, remember the certificate is signed by Global Sign. Sign means using Global Sign private key. So your software, your browser, must have the public key of the certification authority. And of course, this is the assumption that we're making. We're assuming that the software that you use, so like your web browser, Safari, Chrome, Edge, is having the correct certification authority public keys here. So this is true most of the time because they come with the OS. Now, if you install on your machine a given web browser, then you have to make sure that you do it from an authenticated system. So you typically download a new web browser using a pre-installed web browser like Explorer if you use Windows, or Safari if you use macOS. So because the assumption that you're making is that Explorer or Safari, who come with the operating system, contain the correct public keys here. Certificates have a validity time of the order of a year, and they can also be revoked. That means that the browsers should verify the validity of a certificate. So all good browsers like Chrome or Safari do it. Explorer for some time did not always do it, but as I understand now, Edge, which is a replacement for Explorer, does it. So checking the validity of a certificate requires in particularly a clock to be accurate. So this is one of the instances where you need a time that is, roughly speaking, accurate in your computer, even if you don't need the same kind of accuracy as you need when you do PMU phasor estimations. But you need a time, because if a certificate has a validity time and it says it's valid until 2005, if your computer believes it is in 2004, it might take this certificate as valid. That's also an attack against system. By changing the clock, you may induce a system into accepting a certificate that is no longer valid. Because it's no longer valid, nobody bothered to revoke it. The certificate perhaps was using a hash signature that was SHA-1 or MD5, and this hash is now broken. So this is providing no security. And if your system does not have the correct clock and does not verify the time, then it will be weak.
Excuse me?
Yes?
Just a question on the slide. When we see the sign, like the lock on the next to the website, if we see that it's not secure, there is, I think, a triangle with warning sign. Does this necessarily mean that the public key from the website is wrong?
So the question is, what happens if you go to a website and you do not see this green closed padlock or whatever other system your browser is using, right?
Yes, like we are sure that the public key is wrong, or it can be another problem?
No, it can, in most of the cases, it means that it is not secured, so there is no certificate. So typically this is visible, not always, but in practice, that's the difference between HTTP and HTTPS. So HTTP, when you go to a website that is called HTTP/something, it typically means that there is no security attached to it. So there is no encryption, there is no authentication, nothing. So whatever you send to this site, whatever you receive from this site can be altered by a man in the middle. You should not trust anything you see on this site. This was the state of the art 25 years ago when the internet was introduced. All sites were using HTTP because that seems paradoxical today, but when the internet started, nobody cared about security, right? We were living in another world, the world of bisounours, where there were only universities that were using the internet and security was not an issue. Of course, I was extremely naive. And as soon as the internet was deployed, the bad guys started attacking it. And it's like creating houses where there is no key on the doors, right? So that's nice and with some myths, but in practice it doesn't work. And there are still many old sites, essentially sites of association, non-governmental organizations, or old sites that people, individuals are maintaining, and they never bother to modify, to move from HTTP to HTTPS. That may be a reason. There might be also HTTPS sites that use certificates that your browser could not verify. Because why could it not verify? Well, because the certificate is signed. If it's signed by a global sign or VeriSign or an entity that your browser has the public keys of, then your browser will be able to verify it. If it's signed by someone else, and sometimes you can do what is called self-signed certificate, you create an organization and then you don't want to bother making all this expensive certificate stuff. So you can simply download the certificate software and you can sign your own certificate. In fact, we do that in the advanced lab for those of you who do the advanced lab and the security part. Now, if it is self-signed or signed by an entity that is not known by your browser, then the browser will also issue a warning signal saying, I cannot sign this, do you trust this? Or will sometimes guide you into what you can do. But that probably is suspicious. So if it's in the context of a lab or an industrial network, perhaps you can believe the guys are sloppy and it was self-signed because they didn't bother. But still, there is a suspicion that the thing is not secure. To give you an idea, I mean, when you're doing things on the global internet, if you open a server today, if you make it public, and if you install some software to monitor denial of service attacks or port scans, within a few seconds of opening your server on the internet, you will find tens of attacks against your system. Right? So it is not like just in case you do that. No, it's the analogy with the biological world of viruses is exactly the same. And if somebody has a disease with no immune system, then that person is in big trouble and will not survive long if they don't have a special environment. The same is true in the computer world. If you don't have protections against attacks, your system will be attacked, not within days or weeks, but probably within seconds or minutes after starting. So it's very risky to go to a site that does not have this, right? It might be a site that is compromised and that is sending you some malware, for example, through your web browser.
Okay, so there is no way to verify if they just don't have the certificate or if they really are like people that want to do some harm.
Well, you don't know, right? It's like when you receive a mail that somebody you don't know that says click here. It's not 100% sure it's bad, but it's a good idea not to click on the mail that you receive from somebody whom you don't know. So here it's the same. There's no guarantee that it's wrong, but there's a high chance that something that is not using HTTPS today is weakly secured. And as I said, any server that is not secure today is attacked, probably. It's very, very likely that a server that is not protected is corrupted because there are billions of robots that are working in the world trying to deploy their clones into servers that are not protected. Of course, there are cases where this could be valid if, for example, you're doing your own private network, for example, your smart grid, you're installing certificates into your PDCs and PMUs, and since you're doing everything privately, you can sign your own certificates and install them using your own secure procedure. For example, a secure procedure could be that you physically install the software in your company. So you don't have the software, the initial software is not done by an online procedure, but you install the certificates locally by having trusted people of your organization do it. So that's a perfectly valid way of, in that case, your certificates will be signed by your own organization. And of course, you can, with all certification software, you can put the root certificates manually, the ones of your own organization. So that would be a case where your browser by default would not know, but you need to configure your browser to know the certificates of your organization. For example, we could imagine that EPFL gives certificates to some of the internal networks of EPFL and works in this way. I don't think EPFL does it today, but we could imagine that companies do that. Voilà. Does it answer your question on?
Yes, very clear. Thank you.
Good. So now time for another quiz. What does Lisa's browsers obtain from the digital certificate for Lisa's bank? I close in 5 seconds. And here the majority says A and B, which is correct. A and B, which is D here. You obtain the public key and the identity, and this is what will be verified. The public key will be verified using the public key of the certification authority, and the identity will be displayed for the user to read. And of course, you don't want to obtain the public key of the issuing certificate from the certificate itself. You could sometimes, and that's called a self-signed certificate, but that breaks the purpose of the certificate, of course.
Excuse me?
Yes?
I have a question on the public key of the certificate authority.
Yeah.
Is it not a problem that it comes installed on the devices, because it means that it cannot change very often?
Correct.
And is that an issue?
Yes, that's an issue. That's why you need to, you can change them, but you change it changes. Of course, the public key has a certain validity, so it will change at some point in time, but the change will be verified using the existing public key that works. So if for some reason the issuing certification authority disappears, if the company goes bankrupt, then you have a major problem. You will need to, you have a big problem.
Okay, and are there ways to deal with that, or?
Well, as I said, the ways are, as first you have several certification authority, not one.
Mm-hmm.
So I mentioned one, but you have several, and this is for these reasons. So you have a certificate that is signed by, maybe signed by, or you have multiple certificates signed by different certification authorities. If one certification authority disappears, then the others will remain, or at least you can use the other certification authorities to bootstrap another chain of certificates.
Okay.
But if all root certificates that are put into your system, into your software, become invalid, and they have not been used to obtain new certificates that are valid, new public keys of certification authorities that are valid, then the system breaks.
Okay, thank you.
You're welcome. So here we come close to the end of the second hour, but I have only perhaps 10-15 minutes more to go. So what I would propose is to not do a break now, but instead terminate in 15 minutes approximately, if that's okay with you. If it is not okay with you, then it's time to shout or to say no. But I see several approval fingers. Good, so I assume we continue, and then we will finish in about a quarter of an hour. The last topic that we need to see is forward secrecy. So security is always a long chain of things. So first we secure something with secret keys, and we see there's a problem with distributing the keys. So we invent public key cryptography that solves the problem of distributing the keys. But then there's the problem of the first public key, so we need certificates. And then there's yet another problem, which is the following. It is the fact that in the computer world, things evolve. So something that is, as I mentioned already, something that is secure today using was secure using DES or SHA-1, for example, or MD5, later might become unsecure because somebody has found a way to crack the software. And there's, as I mentioned also, there's a big, big risk in the future, which is not 100% certain, but is taken seriously by the industry. That's the arrival of quantum computers. A lot of the cryptography that is happening today might be unsecure in the future. When is that future? Is it in 10 years or in 50 years? We don't know really, but the risk exists. So the following scenario will certainly, or occurs once in a while. Assume an adversary has recorded all the messages sent. So why would somebody do that to you? Probably not to you, except if you're the president of a government or the head of a bank or the head of a big company or an opponent to a government in a company, in a country where opponents are not allowed to speak openly. Then everything you do and write will be logged, copied. And if you are very secure, then all your WhatsApp connections, all that stuff is unreadable, or Telegram connections are unreadable because they are properly encrypted. However, perhaps sometimes later, the keys that were used, one of the keys, for example, if you use RSA, a private key here is revealed, perhaps because you were using a key. That was the case 20 years ago. People would use keys of 512 bits. Now with today's computer clusters, you can break RSA if the key is less than 500 bits, for example. So the attacker is now able to compute your private key. Now, if you have used this encryption mechanism, like with RSA, to send passwords online, then you can decrypt them. And if you have decrypted the passwords, then if the person you're spying upon is not extremely secure, the password might still be in use today. And therefore, you have the password of that person, and then bingo, you have a free lunch, open bar into that person's information. Forward secrecy means that this is not possible. It means that an adversary who has the logs of encrypted messages sent in the past and the private keys that were used in the past cannot decrypt the logs. So that's what we would like to have. And this is justified by the fact that we can never guarantee that something that is used, that is secure today, will be secure in the future. For that, there's a number of systems. The most well-known is called the Diffie-Hellman Key Exchange, or as we will see later, the authenticated Diffie-Hellman Key Exchange. That is a mechanism to exchange a secret in a way such that it's impossible, even by reading all the logs, to gain any information about the secrets that were exchanged here. There are several mechanisms that use that. The ones that are used today use Diffie-Hellman, but they are not quantum proof. So there are other mechanisms that are based on hash that are being developed, that are deployed today, but they're more complicated to explain. So I will explain the Diffie-Hellman Key Exchange. So the problem is that we have Lisa and the bank who want to agree on the secret key L that will be used with AES, for example, and we want to make sure that this key is not revealed, even by somebody who has seen all the communication. How can we do that? Well, it's based in the classical setting on the difficulty of what is called a discrete logarithm. So it works as follows. We use large prime numbers. So you find similar ingredients with RSA. And what is called a generator. So what is a generator? Well, if you have a prime number, let me give an example here, like 17. A generator is a number like 3, such that all the numbers between 1 and 16, so modulo 17, the number are 0 to 16, but 0 here is not interesting. If I took all the powers of 3, so I compute 3 to the power k, for k being all numbers modulo 17, except 0. Of course, 3 to the power 0 gives 1 always, so that's not an interesting case. 3 to the power 1 gives 3. 3 to the power 3, for example, this is 81. Modulo 17 is the same as 10, etc. So we see on the left all the different exponents from 1 to 16, and on the right all the values of 3 to the power k. Here we observe that it's a permutation. All the numbers from 1 to 16 appear exactly once on the right, which is not true for any value of g, but is the theory of finite fields says that there is at least one generator for any case like this here. And the log here means the reverse of the exponential. For example, 3 to the power 7 gives 11. So we can say that 7 is the logarithm of 11 when we take as basis 3. We know all the decimal and the natural logarithms. That's in the context of the field of real numbers. Here, in the context of finite fields, it's formally similar, but of course the details are very different here. So here we see that the exponentiation induces a permutation of the set of numbers that are non-zero. And the theory says that if n is integer, then this permutation appears to be random. So if n is a very large integer, not 17, but a huge number with 1,000 or 2,000 bits, we have a random permutation of the set of numbers between 0 and n minus 1. And finding the discrete log is inverting that permutation, and it can be done, as long as we don't have quantum computers, it can be done only by brute force. So trying all the powers of 3, for example, until we find this one. Of course, my example is by necessity not convincing, because in order to show things, I need a small example. And if I have a small example, I can do a brute force attack. For example, I know in that case, the discrete log, I have simply a table here. But imagine this table is huge. It has 10 to the power several hundreds. So the number is once followed by several hundreds of zeros. So there are more numbers in the list than number of atoms in the universe. So of course, we will not write this list. We can only compute an element in one way, but in the other way, it's very difficult. That's another example of a one-way function. So that's the basis of this Diffie-Hellman method. So when Lisa and the bank wants to agree on a secret key, Lisa chooses at random a number in this list here. For example, here, Lisa has chosen 7. But instead of sending this number encrypted, like we did before with when we used RSA to provide the hybrid cryptography key system, instead I will send the generator to the power of my random number. So I will send 3 to the power 7. So Lisa has chosen 7, but sends in the clear 11. And because we believe that going from 11 to 7 is a very hard problem, because there's more than astronomical number of possibilities, and the only way to go backwards is to do the brute force attack, then we believe any attacker that sees the 11 does not have enough computing resources, unless they are God or something even more complicated. They cannot find the 7. So we send the 11 here, which is 3 to the power 7. The bank does the same, chooses also another number at random, for 13, and sends 12 here. Again, we believe that seeing 12 does not give us any information that the secret number chosen by the bank was 13. So each of them has received a number. And then what they do is they take the received number and they put it to the power of their secret number. So Lisa has chosen 7, has computed 3 to the power 7, has received 3 to the power 13. What Lisa will do is compute the received things to the power 7 here. The bank will do the same. The bank will receive 11 and will put it to the power 13 here. So of course they do different computation, but if we look at the theory, what we have here, Lisa has sent G to the power A, has received G to the power B. Lisa knows A is a temporary secret that doesn't get out of Lisa's machine and will not be visible in the logs. Lisa computes, receive to the power A. Bank does the same, and now we know that G to the power A to the power B is G to the power AB, which is the same as G to the power BA. So those things commute. So we use a commutativity property of this number theoretic environment, and this guarantees that the number that they have will be the same 7. If somebody later reads the logs here, and if the discrete log is still remaining a difficult problem, then seeing the 11 and 12 will not make it easier to find the number 7. As for RSA, that works only if the prime number is very large. And as for RSA, there are variants using elliptic curves. And as I mentioned, there are also variants that are quantum proof, but they are based on slightly different, very different mechanisms here. That's not the end of the story, because our bad guy in the middle will continue to break the system. If the bad guy can pretend to be the bank to Lisa, then the bad guy will establish a secured connection with Lisa and with the bank, and then can pipe all the information, and that breaks, of course, the confidentiality. So this alone does not work. So you need to sign it. So you will still need to sign the number. So the number here, X, will be sent, signed here, and after that we do as before here. Now, if we sign, you can say, well, but that breaks the forward secrecy property. No, because for signing, this was used only for Lisa to make sure that at the time the transaction was done, that Lisa is indeed talking to the bank here. Of course, later, the bank could forge, an attacker 5 years later could forge a certificate, but that is not useful, because what is important here for the signature is that we know that we're talking with the other end here. An adversary who has access to the history of messages, therefore, will not be able to decipher the message, even if the adversary finds the permanent keys. The permanent keys are the RSA keys used for the signature of this exchange here. All the other elements, the B, the L, those are temporary values that are not based on passwords or anything permanent. Voila. What do you think about the two statements I am making here? I close the poll in a few seconds. And the majority says A and B, which is the correct answer. Both parties create the same secret key without ever sending any secret information on the line. That is the purpose of Diffie-Hellman. But Diffie-Hellman requires on the impossibility of solving the discrete logarithm. If that breaks, and this will break if quantum computers are available, then this is not forward secret. So other forward secrecy mechanisms are being proposed, and hopefully most software systems will adopt the systems that are not based on discrete logarithms. Well, we come to the end of our journey of security. Of course, the goal is not to make you security experts, but the goal is that you, who will have responsibilities later as engineers, take security very seriously. Encryption provides confidentiality. MAC provides authentication, but uses a secret key. We have seen that public key cryptography and certificates are able to solve the problems of the key. They provide also authentication and non-repudiation. And, as I hope I have convinced you, a cryptographic method that is secure today will most likely not be so in the future. Therefore, software must be regularly updated, which is a major pain and a major price when we go from non-intelligent system to intelligent systems. And this is why we do this course on security inside of a smart grid course. It is because you must be convinced that this is important. We have spoken of the technical parts of the security, but there are the non-technical parts. Passwords are a huge fragile part of the security today. Passwords must be frequently changed, which is in practice not so doable. So you will not change a password every week, but if you change it every year, that's a good thing. More important even, they must be different for every site. So any site can be compromised because you don't know who maintains the site. Perhaps it's very poorly done. Sometimes you go to shop on the web, you click, I have lost my password, and then you receive a message with your password written in the clear. Then you can be very suspicious of those sites, right? But that happens. Cannot guarantee that will never happen. But even big, serious companies like Google had password attacks, fragilities. So you should always assume that one password that you're using can be compromised here. And as I mentioned, when you implement security solutions or you verify that security solutions are implemented, you should go, for example, to the site of the NIST that maintains the state of the art of what is secure today and what is not. Voila, that's the end for today. I hope you've enjoyed this series of lectures. So for the lecturing part, we will meet again after Easter for other modules on OPF, optimal power flow, and the like. In the meantime, I invite you to do a quiz on security and finish the other quizzes if it's for the few of you who have not yet, and then enjoy the labs.